In this section of material, we're going to start with or talk about sampling theory and estimation. Those are two different topics looking at similar aspects but from different perspectives. The sampling theory turns out not to be as useful as estimation, but the sampling theory, or the understanding of the sampling theory, is important in working with all this material. The more you understand something, the less you have to, or the less difficult it is to learn it, okay, to remember it. All right, sampling. We're start with given population information. We say something important, of course, about all possible samples from that population. Okay, so we start with population information. Estimation is more useful, very simple thing to do, even without understanding anything. And it's sort of the precursor to very powerful tools that we'll see in QM214. In estimation, we turn this perspective around. Instead of given sample information, we say something about the given population information, we say something about samples. In estimation, we're given sample information, right, and we say something important again about the population parameters. Population parameters being like the mean and standard deviation, for instance. Alright, so sampling, we go from population, say something about samples. In estimation, we start with a sample bit of information, and we say something about the population. The sampling theory, our statements are precise in a probabilistic way. Alright, and when we start with sample information and we say something about the population, we have the sample, of course, is a very small part of the population. Our information is complete. Okay, so all of these things deal heavily with probabilities, and hence the probability theory earlier on. All right, but these concepts are important to the working of statistics, and you'll see as we go through this stuff, we will lean heavily on the concepts of mean, standard deviation, variance, and basic probability theory, including the binomial distribution and later the normal distribution. So all these things get tied together now and make this whole thing useful. Okay. In this video, we won't talk about all these things. We will talk about sampling distributions in general, or actually say sampling distributions for the sample average. And we'll talk about something called the central limit theorem. It's not a theorem like, we won't deal with it like a theorem that we've done in geometry or math over the years. It's just a statement which can be proved. Alright. Let's assume a very simple population. If we start with something difficult and try to build on that, things just get harder to visualize. So we'll do this for a very simple situation, and so we can visualize more easily what happens when we take samples. Alright, that's the object in all, or the sort of the mode of operation with a lot of academic thought, and you should try to emulate it yourself. If you have a difficult problem, translate it or make a similar simple problem and see how that works, and then go back to your more difficult problem and do that. Right? That's the mode that we will follow here. So we'll assume a very simple population where half the values are zeros and the other half are ones. Alright, so we could write that as a probability distribution, and that's important to us now. Alright, zeros and ones for the x's, probabilities of a zero, probability of a zero is a half, probability of one is a half. And so we have a complete probability distribution. So this is the probability distribution of the population. Alright, if you want to sort of identify it with anything, this could be like a coin toss, with a 0 being a tail and a 1 being a head. And let's say that we get nothing, $0 if a tail appears, and we get $1 if a head appears. Let's find the mean, variance, and standard deviation of this simple population. Alright, so that's our probability distribution. To find the average, we need x p of x, and to find the variance and then standard deviation, we need x squared p of x. Alright, we've done this or something like it before. Right, 0 times a half is 0, 1 times a half is a half. Add up that column, right, which is denoted by sigma x p of x. This is either called the expected value of x or just the mean, mu. Alright, so the average here is a half, and that's to be expected. We have probabilities of a half on 0 and 1, and so the average has got to be halfway between those two elements, 0 and 1. To find again the variance standard deviation, x squared p of x, so 0 squared times a half, again 0, 1 squared times a half is a half, that adds up to a half, and that's sigma x squared p of x. So we can either call this as v of x, or variance of x, or sigma squared is a summation of sigma x squared p of x minus the mean squared. So the sigma x squared p of x is the addition of the last column, which is a half, minus the average. Alright, the second last column, which is the mean, is also a half, but squared. Alright, so half minus a quarter. And so the variance of our population is a quarter. the standard deviation, sigma, square root of the variance, square root of a quarter is equal to a half. Okay, so for this particular population, alright, just write it down. Alright, this is our distribution. We have a mean of a half, variance of a half, standard deviation. Sorry, I'm doing this wrong. The variance, sigma squared, is a quarter, and the standard deviation is equal to a half. Alright, so this is our particular population, and now we're going to take samples of this population. Okay.